All right, I'm trying to get a couple sample videos out there for you as early as I can today. So we're going to be looking at doing a parallel capacitor circuit right here. So without too much talk, I'm just going to get into solving it. I just want you guys, you've had plenty of explanation and there's been a couple how-to videos. Now let's just do a couple of these problems together. So start off here. I say I have my capacitance and I'm going to want to convert that into my capacitive reactance so I can put that into the circuit. So step one is going to be, let's look at our formulas. And if we're looking to go from capacitance to capacitive reactance, we're going to be using this one right here. All right. So 1 divided by 2 pi frequency times the capacitance. And it's microfarads, right? So I'm just going to write it out as farads so I can put it straight into my calculator. And then I'm going to put it in here, making sure to maintain my parentheses so I don't lose any of my information or my order of operations. Okay. 26.526. The worst looking ohm symbol ever. I think my pen's running out of batteries here. Alright, so I got a good chunk of the information I need down here, so let's come down to the chart. We got the voltage total, 10 volts, resistance of 5 ohms. My XC is 26.526. And then I had 100 microfarads. Okay, so since we're parallel, we got two values in my ohmic category here. Let's go ahead and pull up our formula sheet. So if I'm looking for the resistance total, I'm going to be using this formula right here. So it's a hybrid of our Pythagorean theorem and the reciprocal divided by the sum of the reciprocals formula that we had for DC. So let's go ahead and input that over there. So we're looking for the resistance total, which is Z. So Z equals 1 divided by square root of 1 divided by 5 squared plus 1 divided by 26.526 squared. And I'm going to show you how to put that in on the scientific calculator over here. All right, so we have 1 divided by square root of 1 divided by 5 squared plus 1 divided by 26.526 squared, and then we're going to find the square root of that, and that divided 1 divided by that total. So our total we get here is 4.913. Now, if you remember what we knew about parallel resistance values in DC, if I got a value that was larger than any of my other resistance values, I would know I did something wrong. So this is slightly smaller than 5, so that tells me that that should be at least in the realm of possibility, that answer there, because it's smaller than my other resistance values. So with that observation, let's look at what we can solve for next. So now I have Z and I have E. So if we look at our formulas, if I have Z and E, I could solve for I or the power, which in this case would be the apparent power in that category. So we're going to be looking right here. A lot of these you shouldn't even need to look at the formula sheet for because you should know them. So if I have 10 volts and 4.913 ohms, I know I can just do 10 divided by 4.913, and that's going to give me my IT. So 10 divided by 4.913 gives us 2.035. And then now we can multiply that by 10. Remember, the voltage times the current is going to give us our power. And our apparent power is 20.35 volt amps. All right, there's one thing we know about parallel circuits as well that's going to help us solve this a little quicker, is that the voltage available at each branch should be the same. So now that we got the voltage and we have the resistance in each of these, it should be pretty easy to solve for the current traveling through each branch. So I'm going to say for this category here, for our resistance values, 10 divided by 5, it's going to give me 2. And 10 divided by 26.526, it's going to give me 0.377. Or 377 milliamps. All right, now we can solve for our power in each of those categories as well. So if we're going again back to our resistance category, 10 times 2 should give me my true power, my voltage times my current. So I've got 20 watts. And 10 times 0.377, that's going to give me my VARs, so 3.77 VARs. Okay, that's most of the information. The only thing we're missing now is our power factor and our phase angle. And those are going to be about the very similar process to solve for each of those. So if we look at our formula sheet, we see that the power factor is true power divided by apparent power. So that's going to be 20 divided by 20.35. And that gives us a power factor of 0.983. So we'll just call that 0.98. Usually we only do 2 decimals there on the nameplate datas. And our phase angle would be pretty easy to find. That's going to be the cosine of, so let's look at the triangle. So we can jump, and I'll just tell you right now, we can go straight to the inverse cosine or arc cosine and just put in 0.98. But let's look at y exactly. So if we go back over to our formula sheet, we're looking at this triangle right here. So we said that the true power and apparent power are how you figure out the power factor. So I would take the true power over apparent power. So what type of trig function will I be using if I wanted to use those two sides to find this angle? I have my adjacent and my hypotenuse. So if I had those two sides, which I just divided and found out was 0.98, I would be using cosine. Excuse me, cosine. So if I put inverse cosine and solve that with the true power divided by apparent power of this sides of the triangle, that's going to give me my angle there, which is going to be my phase angle.